So, as the previous speakers did, I'll tell you a bit about how I got into this. I'm really happy to be here. I was at a couple of the public talks, and it was really interesting to see the enthusiasm. I didn't really plan on being this. Sure, I looked at the sky, thought it was useful, interesting, etc., etc. When I wanted to study, it wasn't my plan that I would be studying astronomy. In fact, when I chose a school, it was with the express decision that maybe I'll be studying something else that I wanted, and I'll forget about astronomy. But as things turned out, I realized that there are things that you can measure by looking out into the sky that you would have no chance of measuring in a lab, sitting in one place. And if you're wondering, the kind of things that I was thinking about were the accelerating expansion of the universe, which you'll hear about in, I think it's being talked about in one of the other slams, and there's going to be probably a talk tomorrow on that. But I'll carry forward that thought and probably not give you any new facts today, because that thought can be, you can sort of get that argument just thinking about something that I think all of you have heard about, that the universe is expanding, right? All of you have heard that? Okay. So I just wanted to talk a bit about that and what that means and how that can be measured. So we know of things. I see a lot of young people here, and they grow taller, they expand. And how do you measure that? Okay, so basically what you do is, over maybe a span of a couple of months or a couple of weeks, you have some standard of length, the measuring tape or meter stick, which you think stays constant in time. And you compare the sizes of these growing children and find that that grows. Right? So if the universe is expanding, is that something we can do? Is there a meter stick out there that we can use to measure how far the universe is expanding? So here's where I have to get into a bit of an idealization. When we talk about the universe expanding, we talk about what we call a homogeneous and isotropic universe. Homogeneous is pretty much what you think I mean, right? If you look at some part of the universe and you look at some other part of the universe moving away, it stays the same. Isotropic means if you look in that direction or that direction, you see the same kind of stuff, right? You know that this is not what we see outside, we only see a single sun. So it's not isotropic. But if you were to average everything in the universe over large chunks of space, large means about, say, think about a cube which is a few 100 million light years, right? And you think about that universe, that's actually a pretty good approximation to what we think it's a very good approximation to this kind of a homogeneous and isotropic universe. And that's kind of the context in which we say the universe is expanding. But if it's really that homogeneous, you don't have a meter stick. If some part of that is expanding, so is everything else. So you don't have a meter stick that stays constant in time, or you're measuring the tape. And so you can't really do this kind of an experiment. Right? And we can go a couple of steps back. I said no meter sticks, no measuring tapes. But what really is a meter stick? I mean, we think of it as a wooden stick or a piece of tape which somebody has measured. But you could use something else for exactly that purpose. For example, we know that light coming from a particular object, particular element, has a very specific size in wavelength. That's the same idea as a meter stick. Right? So if we really say that there are no meter sticks, even that wavelength of light cannot be constant. And therefore, it must expand in the same way as the rest of the universe. And that's indeed what people call redshift, because it means that an object which was far back in time, the light that was coming out from that, the wavelength of that light gets stretched. The way you would see this is that its color would look different. And that's one of the ways we know that the universe has been expanding. But I talked about a distant object. Let's go back and talk about, I said that it's hard to do these things in a lab. So in fact, expansion of the universe is something that you could not do sitting in a lab. And let's do what we call a thought experiment. So think about two mirrors and think about bouncing light between those two mirrors. And in thought experiments, you're allowed to think that you're immortal. You've been here forever. There are no technical difficulties. Nobody's going to stop you from doing that experiment because of money or any other challenges that you might have. So imagine that you have those two mirrors and light is bouncing around. And you know that the speed of light is constant, and you have a wristwatch by which you measure time. If these mirrors are actually expanding out, then you should be able to see that the speed of light being constant, it should start taking more time. And so, if you agree with me that this is something that you couldn't do locally, that's how theory has been set up, there's no way of doing that. And the only out is that your clock must not work in the same way. So it's not only just the fact that space expands in the way we are thinking about it, but your clock would also start running slow. And again, all clocks must run slow as time goes on. So we do in fact see this. There are objects that are out there long time back, objects that we call transients or supernovae, that flare up for a very specific period of time. And how long they flare up for is something that we can see is different depending on how old the object is. That's because our clocks run slow with respect to the clock of that object. Okay? So that's, and I talked a lot about how we cannot measure these things. So I just want to leave you with one part of how it is that we do manage to measure these things, because if our clocks run slow, we can't even use light travel time to measure this. But if you have objects that are very different, so now I'm out of that local experiment scope, then that light is actually traveling through different parts of the universe where the local clock is ticking at a different rate from what it is ticking in your hand. And that's kind of the key that helps us know that expansion is going on. And that's what has led to, of course, you have to do a bit more with these kinds of things, work out all the consequences, but that has led to some of the most exciting discoveries in this field.